Well, this is my attempt at distance learning. Oh, I hope it works out okay. I was thinking about our notes and how important they are for those of us who are moving on to AP Biology our senior year. And so I feel that for those folks, it's important to keep that going, to keep the notes going. So I'm going to do that. As well, I'm going to attach several videos that I want you to watch in order because they're going to show parts of what I'm trying to discuss with you in these notes. So we're just going to give it a shot and see how it goes. I want you to know that I do miss you though, and that obviously this would be a lot easier if we were in person, and maybe not your favorite thing to do. But remember, these notebooks are still going to be worth the extra credit. I am going to figure out a way to grade them. I'm not sure exactly how, but we're gonna get that taken care of. And so you're still gonna want these points when they come around at the end of the semester. Okay, so obviously I think it's a good idea to review what we've talked about since the beginning of this particular chapter. Maybe we should take a minute and go back over the natural selection stuff too. But for now, I want to focus on speciation and get through the notes that we've already taken, and then draw a couple of curves, some survivorship curves. I have the lecture notes, and I'm going to attach them as well. I can't get them to open on my phone. I was going to have them in the background so you can see them, but for whatever reason, they're not loading. So I'll just attach them as Google Slides, and then that way you'll be able to open them up and look at them if you want to. Of course, I don't suppose you have to. But I don't plan on getting much further than a few graphs today. Okay, so we're talking about speciation. Remember, that is when a new species occurs. So you have one species, and over time, it diverges. Remember, diverge means to split. It diverges into two separate species. Now, how does that happen? Well, there's actually more than one way it can happen, so we're going to talk about that. But before we do that, we have to go back over population genetics, which is, remember, looking at a population and all of its alleles together and kind of excluding the individuals. So not looking at the individuals, but looking at the whole population and the genes that it contains. All right, because populations have variation. And what that means simply is that no two individuals are the same, well, unless they're clones of each other, but we're just going to discount that. What causes variation? Oh my gosh. Well, mostly it's mutations, because remember, mutations can be good. That's God, not good. Let's see. Good. They can be bad, or they can be nothing. They can be neutral. And those mutations then are passed on by heredity, and they can be mixed around through recombination and the random fusion of gametes. But environmental factors are going to play out on those mutations and either select for them or not. So if they don't select for them, then they disappear out of the gene pool. Or if they're neutral, like they don't matter, they can sit around, like let's put a little W in that gene pool, they can sit around forever because, you know, they're unknown. They're not being coded for. Or if they are being coded for, it just doesn't matter. Cup of coffee. Okay, so all of the available gametes in a population is called the gene pool. And so it's like you threw all of the alleles, good, bad, ugly, neutral, all of them into a pool, and we just said, okay, so it's obviously a thought experiment. It's not real. It's just a way of looking at your alleles in your population. All right, but we'll come back to this. So I'm going to turn the page. Okay, so those guys, Hardy and Weinberg, these guys down here, they came up with this idea of genetic equilibrium. Genetic equilibrium is this hypothetical population that doesn't really exist, where from generation to generation, the genes in your gene pool don't change. And that would be an equilibrium because, you know, everything is staying equal from generation to generation. So that's what that word kind of implies. So basically what they're saying is in this hypothetical population, all of the alleles are going to stay the same. And we're not going to add any alleles. We're not going to take any away. They're all going to equally reproduce. So we're always going to have the same allele frequencies from generation to generation. But Hardy and Weinberg point out that in order to maintain genetic equilibrium, in order to keep that situation the way it is there, we absolutely positively cannot have any mutations because, like we said before, a mutation going in would wipe out an allele and thus change, or add an allele and change the way that gene pool is represented. You can't have any migration because if a couple of alleles take off, that changes the gene frequency in the gene pool, and that kills it. So also the very large population. That we're going to talk about on the next page, I think, where we, if you recall, we talked about the lupins on the hillside in Lassen and how just a small random chance something can come along and disrupt that gene pool. And it could be really small or really large. Yeah, and also if you did find the time to watch the Island Fox video that I posted, that's going to be important because I'm going to refer to that. So I think it's like 6 minutes long. Please just watch that because I want to be able to bring those island foxes up as an example. And I'll talk about them too. So individuals must mate randomly. So that means no sexual selection. And that turns out to be a really big force for selection because, you know, if you can't pass on your genes, then, you know, you don't get to have those offspring and your genes don't move on to the next generation. But not only that, those who do get to pass on their genes, well, duh, they have their genes in the next generation. So we'll talk about that as well. Okay, and this is the last one. You can't have natural selection. So it doesn't take a brainiac to figure out that this isn't possible. It's not real. So genetic equilibrium doesn't exist. And gene pools do change over time. And I guess the point of that is that evolution is a change to the gene pool. And so therefore evolution is occurring constantly and all the time in all populations. Okay, so what do we have here? Mutations. This is our examples of mutations. And if you want to think back, we watched the sickle cell anemia. There's a video right here. And that is the HHMI sickle cell anemia video. And if you've forgotten that, go back and rewatch it. And it talks about how mutations occur also that lead to that sickle cell anemia and how evolution works with that. It's really interesting. But aside from that, I want to point out that there was also the HHMI pocket mouse video that we watched, and we turned in a worksheet for that. But this pocket mouse one talks about how a mutation can occur. Remember that light coat color in the mice and the dark coat color in the mice. And then after that occurs how selection occurs to those mice and how it can change a population. The thing that's interesting about the pocket mouse population and the sickle cell anemia population is that they're still the same species. Speciation hasn't occurred in those cases. Just mutations in natural selection has occurred. So what we need to look at is how could those mice become separate species if enough time has passed. Okay, but that's not today's talk. We've got different types of mutations. Remember, we talked about different types of chromosome mutations. We can have deletions. Did I make a list of them? No. There were deletions. Oh, I'm sorry. That's hard to see, isn't it? And there were translocations. Different things that can happen to chromosomes so that mutation occurs. And I know that there's some examples that we want to talk about, but perhaps not right this second. Okay, we also talked about migration and the different ways that genes can move into or out of a population. And we primarily used plants as an example of that with their pollen. But the same can be true of animals moving into or out of a population. Okay, genetic drift was our last thing we talked about. And again, this is where you have a small population and it's subject to random chance. And we told the story of the lupins and Lassen and how a random chance event could occur and lead to problems or extinction of certain alleles, maybe not the whole population, but alleles out of the population. Okay, that's all fine and good. So here we are, we're on to a fresh piece of paper or moving down our spiral notebook. I am almost completely out of paper, so that'll be fun. Okay, so we are on objective 8 on your objectives. Contrast the effects of stabilizing, directional, and disruptive selection on variations in a trait over time. So we're gonna draw 3 graphs and we could draw them like this. Let me see, I'm gonna try to keep straight, so I'm gonna move my chair. Okay, so we're gonna draw a box. Ooh, okay. And in that box, what I want to do is just draw a regular old bell curve. So this is going to represent a normal distribution in a population. So going back to bell curves and our discussion of how variation in a population can give you very, well, depending on the trait, so some very small individuals, some very large individuals, but the majority of individuals are going to be in the center of the bell curve. All right. So I'm going to make the center, I need a pencil sharpener. That would be nice, wouldn't it? Okay, oh, look at that. See, that baby just broke right out of there. Glorious. All right, we're gonna go with green then. All right, so there we have a normal bell curve. And what we want to illustrate in this box is the first one. And if we look at objective 8, the first one is stabilizing selection. That's S-T-A-B-I-L-I-Z.